freshman year in Project Lead the Way, we learned a lot of basics about designing solutions. And so we learned about the design process, which is something that we've been using all the years after that.
We spent a lot of time modeling, physical models, mathematical models, and also software models. And the things that they're able to do at the end of the first year in modeling just amaze me.
The Project Lead the Way program really taught me a lot of mechanical skills along with electrical and programming, all the disciplines of engineering.
Really, it's about creativity and kind of just having the ability or the willingness to work through ideas and to really get into things and examine what's going on, how does this work, can I make it better, how could I do that, and what are some great ideas that that might help solve different problems of the world.
We've also learned how to work together in groups and brainstorm, which is something that's really important to do, especially in an engineering career in the future.
It's helped me strengthen my thinking process so that I can go on to college and to these mechanical engineering field and be able to, right out of the gate, know how to think and know how to process things and know how to communicate to other people my ideas.
It's just given me a head start in a lot of the disciplines of engineering that are taught, like mechanical, electrical, and programming. So going into the next step, I'll have a lot of background knowledge about those topics.
I think having background knowledge coming into studying engineering, it's like a big advantage.
The lead up from the past 3 years to this year has been the most incredible journey because we've been able to take the curriculum from the past 3 years and use that to become very good at what we're doing this year.
The highlight of the program for me is really this fourth year capstone course that I'm currently participating in because we get to put all of the skills that we learned in the past 3 years to use in one final project throughout the entire year.
Being in this course is one of the best things academically that could happen to you.
I think that the program has really helped me learn about different types of engineering and lots of different aspects of things that are very applicable to other mathematical and scientific fields.
So you're going to use these tools now that you've acquired to then make more technical sketches. Again, they're not going to be perfect because these are brainstorming sketches, but you're going to use these to move forward.
PLTW has prepared me after Seneca, not only in problem solving, which is a huge thing that we do here, but also in time management.
Being a Project Lead the Way teacher has helped to kind of broaden my world a little bit. It's let me look out into the bigger world and see where science, engineering, technology kind of all come together to solve bigger problems.
Rather than just teaching them how to do something, I find myself thinking about the inherent science and math concepts and trying to draw those out.
I think that my highlight of the Project Lead the Way program is just how much it's taught me in terms of my future career. I've realized that I want to go into an engineering field because of this class.
The things that we got to do in this class were so beyond what we would be able to do in a regular drafting class or really any class you could have taken at Seneca because of the resources that we have.
I think they come out with empowered to be engineers. They understand the fundamentals of what different engineers do and how to use those skills to make things happen.
Hello everyone, welcome and thank you for coming to see what our amazing Seneca seniors have accomplished. I am Mrs. Dusty Carroll, their senior teacher. First, I'd like to take a moment to thank our panel of engineers who have taken their time to give feedback and help to the students throughout the year. If you guys wouldn't mind standing up when I say your name, and then we're going to clap for you. Mr. Scott Boisvert. Oh, we'll clap now. Mr. Jeff Warner. Mr. Bob Lindaberry. Mr. Rob Countess, I'm sorry. And Mr. Alex Whitney. So this panel of engineers has been in contact with our students throughout the year. They have been sending them updates and websites and just ideas and pictures, and the engineers have given them lots of great feedback, lots of good ideas, some resources to follow through with, and so they've been a great part of this program, and the kids have really gotten a lot out of their help, so we really appreciate them. We also want to thank Mrs. Heather Zanakis and Mr. Dave Mayer for their unparalleled support for this program and its students. They're amazing. The students and I really do appreciate just everything that they do to ensure the success of this program. They're very helpful. They find a way to make things work when we need something, and they just say, all right, well, we'll figure it out, and we do it. So we really appreciate that. So thank you, Mr. Mayer and Mrs. Zanakis. And I'd like to thank our custodial and tech staff because they really did a lot of work to help set up our cafeteria area, which you guys will see after these presentations. There's a lot of posters and tables and cords and stuff that needed to be set up, so we really appreciate all the time that they took. And especially thanks to Mr. Kirk Seeley, who's up in the booth right now. He handles everything computer related. He makes everything work. He helped me with all kinds of stuff, and he spends his time to come here and just make sure that everything is smooth, so we really appreciate him. Okay, and now I'd like to introduce Mrs. Heather Zanakis to say a few words.
Good evening, and a big thank you for everyone that could come out tonight. On behalf of the Lenape Regional High School District Board of Education and the district administration, I would like to welcome several special people with us this evening, and I ask that you hold your applause till the end. So tonight joining us we have from our Board of Education, Mr. Sam Green, Supervisor of Math and Science, Mr. Mayer, as Ms. Carroll pointed out, our Project Lead the Way teachers, Tom Zanakis, Ashley Vorwerk, Rich Watson, and of course, Ms. Dusty Carroll. And we would like to thank our sponsors who have generously donated finances and time and support to this Project Lead the Way program throughout the district, and they are Lockheed Martin and BAE Systems, so thank you to them. Tonight is a monumental occasion for these students, as this is the culmination of 4 years together as one cohort of students as they've journeyed through this program of Project Lead the Way, and they began to pave the way for all the future students. They began this journey together as freshmen, probably not knowing what exactly would lie ahead, and now 4 years later they are ready to show their friends and family what exactly they have been working on for the past year. Students, congratulations, and we're really excited to see what you have been working on and see your designs in action. Next, it's my pleasure to welcome back to the podium Ms. Dusty Carroll. Thank you.
So every PLTW cohort is unique, and they seem to develop sort of a whole class personality. And so this year's group, the label I would give them is the socially and environmentally conscious, and you will see why once you start seeing these presentations. In the beginning of the year, some of their potential problems just spanned all kinds of topics. So some of the ones that we ended up not pursuing were issues related to driving safety, trying to fix school-related issues like finding ways of reducing stress on the mind and the body, finding more efficient ways of studying and taking notes, thinking about ways of maintaining Wi-Fi in a power outage, fixing minor annoyances like takeout food that gets cold too fast, and brain and medical issues like addressing vitamin D deficiency, solving forgetfulness, and curing headaches. Wouldn't that be fantastic? Through their research, they did a lot of preliminary research, and they ended up ruling out these ideas for a bunch of different reasons, and eventually they settled on some problems that they thought were reasonable to address in our time frame. So part of the selection involved finding out enough about the problems that they had to decide whether they would fit the format that we have. And so tonight, you're going to hear the highlights of their work from throughout the year. They do this time have a designated cutoff time, so I promise there will not be any 40-minute presentations tonight. We should be through here in about an hour, and then we'll head to the cafeteria. So I do hope you enjoy the presentations tonight and that you feel the same pride as I do in our students' accomplishments. So our first group I'd like to welcome up to the stage is our composting group, Mr. Owen Levitt and Shannon Preble.
So our problem was that current methods for separating compostable and non-compostable trash are inefficient and ineffective. Nearly 50% of the material in landfills is compostable. And when compostable material is in landfills, it often doesn't compost correctly, or it composts anaerobically, which releases methane, which is a very potent greenhouse gas. So as you can see, the United States composts between 0 to 5% of all compostable material. And composting would reduce the amount of trash in landfills and the amount of methane produced, so both are very beneficial to the environment. So this is a drawing of our final design that we made on a program called Inventor. So as you can see, we have 3 separate compartments, each with a glass tube in them, and then dividers. The floor also has a section cut out of it because it rotates. So this is the top compartment that was not featured in our inventor drawing. The point of this compartment is to make sure that trash is put in one at a time, because when trash is put in more than one at a time, it gets difficult to determine which piece is compostable and which piece isn't. So we decided that one at a time would be more efficient and more effective. So our dividers, we made these on a program called Xcarve and then had them cut out. And when we originally made them, we had to make some modifications because they didn't quite match our design. When we were making it in real life, we had to cut out some extra pieces and make it fit a little bit better. So, you're good. You can see in the picture we had to have little notches in there, and that was just to make sure that nothing broke the machine and all of that. So in each chamber that we have, in each of the 3 chambers, we would have a sensor that would allow for quick and accurate readings based off the trash that's in the chamber. And if it is compostable, then it would go to one section, and if it wasn't, it would go to the other section. So the glass tubes, they had to be glass because glass does not absorb UV rays, which a lot of plastics and other clear material does. And it also allows for a 360 view with the sensors and lights. And we actually had to add brush to the bottom of these to make sure that the glass wasn't rubbing across the base of the floor, but to also ensure that no trash or anything else escaped through the bottom. And for the separation, the floor had a 1/3 cut out of it, and it would rotate if the section if it was deemed non-compostable, the floor would rotate out and so that the trash falls into the correct position. We had to make sure that these floors also had a sensor to make sure the trash wasn't too large, and if it was too large, then the floor would rotate out into the beginning where it would go into the non-compostable bin.
Okay, so one of the most important components of our design was the UV sensor, because this is what actually is determining whether or not something is compostable. So everything that is compostable has a compostable certification stamp on it, and so we would just put this ink in along with the normal ink used, and there would be a UV sensor similar to the one seen on the screen that would determine if there is the ink present or not. We were not able to get one of these sensors, so we weren't able to properly test it, but we would have to get one for the actual product to test that. And then we would also use light sensors, which would be used to determine when the trash can was full. So in each compartment, there would be a light sensor, and if the trash got too high, it would block off the light sensor, which would then send a signal to a light outside of the trash can, which would then start blinking to alert someone that they needed to take that, empty out that compartment. And then we also did several tests with our prototype, the first being a luminescence test to determine how far the sensor could be while still being able to detect the ink. Because we weren't able to get the actual sensor that we would be using, we had to use much weaker sensors and ink, and with so we weren't able to get as accurate results, but we still were able to figure out what we needed for our prototype. We did a force of friction test to determine how the trash being pushed along the floor would affect the ability for the dividers to rotate. And we also did a survey to determine how willing people would be to use our device, given that they had to like throw things out individually or dump out liquids or follow other similar rules. So with the luminescence test, we found that at a distance of 2 centimeters was when it started to, the intensity started to lower to the point where the sensor wouldn't really effectively pick up the presence of the light. So from that, we determined that our glass tubes for our prototype had to have a diameter of 4 centimeters, so that no matter where the trash was in the tube, it would still be able to be detected. And then for the force of friction, we found that only 2.5 grams caused it to stop, so we would need a much stronger motor than what was being provided by the fan that we used for that test. And we also determined that the glass tubes needed to be lower than they were in our prototype because with our spoon, it got caught underneath the divider, which caused it to stop only 2/3 of the way through the revolution. And for the survey, the graph on the left shows the results when people were asked how likely they were to compost if there were 2 separate bins and they had to separate them out themselves. And the second graph shows the results for if there was a device similar to ours that separated out for them, but they just had to comply to certain rules. And from the graph, people were much more likely to compost when it was done for them and they didn't have to consciously think about it and have pre-existing knowledge as to what was compostable. And then we just have a few acknowledgements. Dr. Hewitt and Dr. Hanna are members of a chemical company who provided us with a lot of helpful information during the preliminary steps of our project. And they also helped us limit out a focus on food as that was accomplished by many other companies already. Mr. Kirk Smith filled out a survey between our 3 final solutions to help us narrow down what direction we should go in. Mrs. Bonnie Horner provided us with the UV light box we used for our luminescence test. Mr. Tom Seneca helped us a lot with our inventor drawing and creating the animation that we have at our display. The engineering panel gave us a lot of helpful insight as to how to progress with our design. And then I forgot to add Mr. Jason Pittner, who he helped us a lot with the X-Carve and the 3D printer to create the components for our prototype. And then the next group that we'll be presenting is the installation group.
So what's the problem that we're trying to solve? Around the country, only about 40.2% of all tires that are disposed of are actually recycled. And if they aren't recycled, many times they're just put in landfills, and in landfills, they take up a lot of valuable space that can be provided for other things, and it also provides a breeding ground for pests like mosquitoes. And right now, there are ways that tires are used currently, disposed of, but a lot of them aren't really the most environmentally friendly. Like there's tire-derived fuel, which is something where you just burn tires and take the energy provided from that to power something. It still releases harmful chemicals that would be released if you were just burning them regularly. Okay. So how do we solve it? We kind of moved towards an idea that would make use of a large quantity of tires at one time. We took inspiration from several things that are currently done, like rubber mulch, which is just the type of stuff that you would find at like a playground or in someone's garden if they wanted to use it. Aggregate is kind of a replacement for construction aggregate, which is used on like roadways in like building construction for foundations and stuff. And crumb rubber it's finely ground up and can be kind of melted and formed into the type of thing that you also see in playgrounds. So the ideas that we initially had was something along the lines of gutters and piping, actually molding crumb rubber or rubber mulch into something that would fulfill that purpose. insulation, which we moved towards in the end, and childproofing and soundproofing, which would also have required a sort of molding that we just wouldn't have really been capable of in our class.
So what we eventually ended up deciding on was creating something based on insulation. And the two main things that we were really trying to accomplish from this, the two main things that we were trying to accomplish with our solution were basically that we wanted to solve another problem in addition to solving the tire recycling problem, and we wanted to use a lot of tire rubber at once. Because the numbers of the amount of recycled tires do not fully solve the problem that's currently existing for tires right now. There are 250 to 300 million tires that are disposed of in our country every year. And like we were talking about earlier, only 40% of them actually get recycled. So that 60% that's not being recycled is just sitting around, and it's just harming our environment, and it's taking up valuable space. So we want to take access from those tens of millions of tires of material and create something from it. And we saw the best way to do that as doing insulation. And we saw that some of the factors for doing this was because we did some research and we found out that rubber is actually already used in piping systems across our country. Rubber is a natural insulator normally, so it actually does trap heat just by its properties as a substance. On a mass scale, we'll be able to use this a lot because houses and buildings are constantly being built. It would be constantly be able to be used in things that need piping. So it's just a constant need in our society today. So we would see it being implemented a lot. And it was just the idea that we generally thought would be able to be implemented properly, both in our classroom and in the world. It was actually our personal favorite out of the ideas that we had. So for our testing, what we ended up doing is we made sort of a quilt device from our tire rubber. We took actually some old lab coats, and we took one on top, one on the bottom, and we made 9 equal squares filled with tire rubber. We got rubber mulch from Amazon, and we actually took a certain amount of it in each pocket, and we put them in so that they were in equal spaces throughout the blanket. So what we essentially had was a quilt filled with tire rubber. And what that did was it protected it from the outside, so we didn't just have loose rubber being covered by foil, and it would protect it in the case of a fire. Because one of the main problems in using tire rubber for anything is that it's flammable. But in our design, we use something to cover it that isn't flame resistant, but in our final design, we would be using something that's flame resistant. The normal heats that are used in heating and ventilation systems aren't nearly enough to make it just catch fire on its own. But if the building were to catch on fire or something, we wanted to have a material to cover it to ensure that there would be no issue. So basically what we did is we actually got some help from one of our physics teachers here at the school, Mr. Seneca, and he told us that the best way to do this was to funnel the heat in through some sort of external pipe and then have it run through the pipes that we were trying to test. So what we have right here, it's a little bit hard to see over there, is we actually had a heat gun. We had it pointed from about 1.5 feet away from the pipe we were actually trying to test. And we had a cardboard tunnel system that we basically pointed it through so that it wouldn't be too hot going in. We wanted to make sure it was around the temperature that you'd normally see in heating vents, which is about 100 to 200 degrees Fahrenheit, and coming out of the gun it was like 400 degrees Fahrenheit. So we didn't want it to cause any issues in our classroom. So what we eventually ended up doing is we had it go through that system. We had a probe at the beginning of the pipe so that you could measure the temperature there, and we had a probe at the end of the pipe so that you could measure the temperature of it coming out. And what we were going to do from this is we'd do different trials for the different types of blankets we were testing, and we would find out the average amount of temperature that you'd lose across the pipes. So from a bunch of trials from that, we'd be able to figure out what's the best insulator. We actually tested 3 different types of designs. In addition to the normal insulation that you can buy at a store, like at Home Depot, it's made out of fiberglass. We made a blanket that was just full of tire rubber. We made one that was less tightly packed so we could test air as an insulator. And we actually made one that was almost double quilted, where we filled in half of the rubber on one of the quilts, and then we stacked it on top of another quilt that had the other half of the tire rubber filled in it, because we wanted to see what would happen if we layered it on top with some of the blank pockets filled with air. So if you look at our final data that we received, we did 10 trials for each of the 4 types of insulation that I was talking about. And we actually found that through all of these trials, that rubber as a natural insulator through all of this was better than the fiberglass insulation that you can buy at stores. So from all of this, we found out that even the double quilted design that had the extra air pockets that I was talking about that you could actually help to further insulate it did a better job than the fully filled one that was just tire rubber. So we need to do more tests to fully determine which one of these is better, but we think that this is a really good start and that this rubber could actually be used in settings that fiberglass can't and actually can be more effective in helping our environment out in the best way possible. One of the things that it actually has above fiberglass as a whole is that fiberglass actually absorbs water, so you could use this sort of rubber insulation underground or in places that there are water because there wouldn't be that sort of risk of the fiberglass being ineffective. So we have a lot of uses for this rubber insulation and we're trying to find the best way to move forward with it. We just have a couple of acknowledgments. Like I was talking about earlier, Mr. Xenakis really helped us finalize our testing procedure for this. We didn't really know what the best way to proceed with it was, and we wanted to make sure that we went through it in a way that didn't have it affected by like the outside temperature in the room. So he was a really big help with that. Ms. Carroll really helped us finalize our quilt design. We wanted to test the air insulation in some way, but we didn't know how, and she really helped us finalize that quilt design that you guys saw up there. And the entire engineering board really helped us with the specifications for our design, especially with the covering that's flame resistant. They pointed out a lot that we wanted to make sure that our device would be safe for consumption, so we wanted to make sure that we prioritized having something that protected the tire rubber from outside uses in our final design. And we'd like to thank ourselves because we did a good job.
All right, so our problem was that we found that when throwing discus, there was only a couple ways that you could actually go back and analyze your throw and try to figure out what exactly you did wrong and how to optimize throwing. We had found that you could use video recording and then go back and look at the video and see how well you threw, which wasn't very accurate, or you could just try to throw better. Next slide. Okay, so we found that this was a problem, and we've shown that it is important to get the exact information because there are very specific different numbers that you want to achieve. Whether when you're throwing you want to throw at a certain angle, a certain speed you want it to spin at a certain rate when you throw the discus, and a certain height you want to achieve when throwing in order to maximize the distance that you can get when throwing a discus. And that's why it's very important to be able to go back and see the data at what angle you threw the discus at, or how high you threw it, or how fast it went. And that's why it's very important to figure this out for a throwing perspective. So these are possible solutions. The first one was the paddle thrower. That's what we called it. So basically it would be a PVC plastic ring that would get set up around the discus ring when you throw, and you would have to basically high five all of the different paddles in the thing. And this was, we had the pros of that it had no electronics in it, so you could use it literally anywhere. You wouldn't need to connect to anything, you wouldn't need to charge it, but it had the downside of not actually giving you much accurate data, so you could go back and see what you did wrong. It didn't affect your footwork, and it was just overall not what we were looking for as a solution.
For our second solution that we were considering was an embedded sensor right inside of the discus itself, and we thought this would be really accurate and useful because you could then get data back directly from the discus itself because the sensor would be inside the discus, getting the direct data as it moves. Some of our concerns with this were that having a sensor inside of the discus would be maintaining the connection with whatever your device you're receiving the data on, because the discus is made partly of metal and it could interfere with the connection as well as you're throwing the discus how far do you throw a discus?
100 feet.
Yeah, about 100 feet away. You're worrying about it losing connection over that sort of distance. And then lastly, our third idea was for net-mounted sensors, where you would set up a net around where you throw discuses, and on the sides of the net would be sensors. And as you throw the discus through the sensor net, it would measure how long it was in the sensor net, so you could find out the speed of the discus, and depending on where it was, you could tell the angle of release from the throw, and so that would also provide feedback. But we decided that this idea was not really worth pursuing because because it's basically the same thing as the previous methods of using cameras to measure the discus, because you still need really expensive sensor arrays and lots of sensors on the sides of the net when you're basically still just buying a lot of expensive equipment and setting up on the sides and checking the data afterwards, and it isn't as accurate as having a sensor inside of the discus.
So this is our final design. We went with, like Robbie said, the embedded sensors in the discus because we thought it could give us the most accurate data, and that it would also be the most convenient for the user too, since it's all in one system. You could connect to it on your phone and you just throw the discus, and wherever it lands, it'll give you the information. So that's just a regular discus. That's what we use to try to build our product around. That's an expanded view next to it of the different parts. In the middle, that gray ring is actually where most of the weight of the discus is. It's like 98% of the weight is in there. So our plan was to replace the center core, which basically just holds the discus together and adds a little bit of weight, with a MoveSense sensor, and that was what we designed. On the far right was the piece that would actually go in the discus, and it would have foam on the top and the bottom of it to actually protect the sensor, and then the sensor would be enclosed in it, and then that would go in the center of the discus to collect data when it was thrown.
So in order to reach our goal as a group, we decided that we need to acquire some sort of sensor. So we contacted this company called MoveSense, who creates sensors just like the one that you see up there. And basically it fits right inside of the discus itself, and it can track several different things such as acceleration or angular velocity, or even like heart rate. So we basically put this inside of the discus with our solution, and we're able to throw the discus in order to track. We just ended up going with acceleration, and it became basically a really key part to our project. So this is a prototype that we created. We used a 3D printer to print out a piece that can protect the MoveSense while the discus is being thrown. So we used some memory foam and packed it inside of a piece that we 3D printed. And the MoveSense sits inside of there, and it's completely protected. We did tests on this, but we ended up having to use, like the image on the right is just memory foam. We had to use just memory foam inside because our 3D printer couldn't create a piece that exactly fits inside of the discus. So we ran into a big issue there and had to move on with our process and do testing without actually using the final product that we created in the middle.
So in order to connect to this MoveSense sensor, it connects through Bluetooth to your phone. I decided to develop this in Android. Now, most of this was using just sample code off of their website to help build this app. And so you connect to the MoveSense sensor, and then you basically just hit the subscribe button for whatever sort of data you're looking for. And then it returns, as the discus constantly updates, it constantly sends a feedback back to your device and records it in a graph. Now, in the future, instead of just recording it to a graph and saving it as a data file on your phone, we plan to have it upload to a cloud of the data from all of the users so that we can get feedback on what the very best throw you can get. So as you throw the discus, it'll measure the angle you release at and the speed at which you release it, and the rotation as you release it. And using a combination of these qualities, we can then find what the ideal throw is and give you feedback on how to better improve your throw for your next throw. And then we have some acknowledgements. We would like to thank Ms. Carroll for helping us out with all of our projects. And then all of the teachers, we asked for surveys, and we'd like to thank the engineer panel for working with us to help further narrow down our ideas and help us develop our designs. And then lastly, we'd like to thank Suunto for sending us their MoveSense sensors.
All right, so I'm Scott Johnson, and I'm going to Georgia Tech next year to study chemical engineering.
My name's Jimmy Pronchek. I'll be going to Bucknell next year. I'm not sure what I'm studying.
I'm Taya Gilliland, and I'm going to Rowan College at Burlington County for liberal arts and sciences because I'm also unsure. So when we initially started this project, we had set a goal, which was to improve the overall health of the homeless and create a solution that would address either one of the issues that they faced, which was with financial or food insecurity, hygienic stuff, or like shelter.
So eventually we were able to narrow our ideas down and focus solely on the oral health of homeless people, and we decided our goal was to create a small mint that could be easily distributed to the homeless and that would act as a substitute to a normal oral health routine, which a homeless person could not have because of the issues they face. Now Scott's going to talk about our brainstorming process.
So this is just the process of how we got to our final goal. We started off with a mind map where we put homelessness in the center, very broad, and then made it specific. Anything related to homelessness we wrote in. And then we got a piece of paper, and for 5 minutes we just came up with any idea that solved one problem the homeless people faced. We then presented to fellow classmates, and from their feedback we picked our best 5. And from our best 5, we put it into a decision matrix where we put criteria and different weights of the criteria, and we picked our best 3. With our best 3, we then dived deep into research to see which one we thought we could do for a whole year and which one would solve the most significant problem. And that's how we ended with the anti-gingivitis mints. I'm going to pass it to Jimmy to describe our first test.
So once we decided on the mints, we began testing the ingredients that we used. We did this by swabbing bacteria from our mouths and growing it in petri dishes. We then inserted different ingredients from our mint into the petri dishes and determined how well it was able to kill pre-existing bacteria. We did this by counting the amount of colonies that grew before the ingredient and then counting again a few days later. Our data, however, did not show that the ingredients were able to kill pre-existing bacteria. We think this could have been because of an issue with the ingredients not mixing into the petri dish well enough, but either way, our data did not show that the ingredients could kill pre-existing bacteria. But now Tay is going to talk about our bacteria prevention test.
Okay, so we did this test by mixing in our intended ingredients into the agar gel before trying to grow the bacteria. And then, so we swabbed the bacteria and put it on there, and the control was covered in colonies, but for our ingredients that we intended to use, there was nothing, which was a successful test. That's what we wanted.
And then our third test was just a simple plaque removal test. So we ate a plaque indicator, which turned anywhere there was plaque blue, as you can see through the pictures. And then we ate one of our mints. Our mints had ridges like engrooved into them, and then when they dried, they were hard. And as you can see, when the mint was moved around, it removed a significant amount of the plaque indicator, meaning that a significant amount of plaque was removed from our mints.
So now we're going to talk a little bit about what actually our final design is made up of. So we included peppermint oil and clove oil because they're antibacterial and anti-inflammatory. We included calcium powder in order to strengthen tooth enamel. And then the base of the mint was just gum paste, which can be molded and then will eventually harden.
We also use xylitol rather than powdered sugar because it's a lot better. It's a lot better for your teeth than real sugar. It's safe for diabetics, and it's naturally found in fruit and vegetables. So, and naturally bacteria in your mouth feeds off of glucose from the food that you eat during the day, and the xylitol prevents the bacteria from doing that, and the bacteria can't eat the xylitol glucose because it's not glucose.
So based on the ingredients we used, we calculated like an estimate price per mint. The mints were relatively small, weighing only about like 11 ounces, 0.11 ounces. And these prices are based on retail prices. We didn't buy in bulk, and we figured if we buy in bulk and produce more mints that the price would go down from 11.5 cents. And for distribution, we came up with an idea that we could just sell them to the homeless shelters, and then they would distribute it to the homeless people rather than just handing them out, because that would be long and inefficient. And just some acknowledgements. We'd like to thank Miss Carroll for all the work she did. She got us all our ingredients, helped guide us when we got lost a little bit.
We also want to thank Mrs. Gardner, a counselor at Seneca, who we contacted throughout the year for feedback.
And then Mrs. Norton, she is like head of the cafeteria, and she gave us aloe for our testing, and she also let us use the cafeteria kitchen to make our prototype mints. And we also want to thank the engineers for all of their feedback and helpfulness.
So next is the windshield ice group. Thank you.
All right, I'm Cole Lodwikowski, and I'm going to Rowan College at Vernon County, and I'm undecided.
Hi, I'm James Hill, and I'm going to the University of Delaware to major in landscape architecture. Okay, so our problem was the consequences of windshields freezing over overnight, and we found that windshields freezing can cause you to be late for work and can also cause accidents. So we wanted to focus on preventing ice from freezing or removing it. And we found that in the 48 contiguous US states, the average temperature in the winter is 33.2 degrees Fahrenheit. So that shows just how cold it gets everywhere. So this problem affects the majority of the United States. And we also found many police reports reporting accidents caused by obstructions to the windshield, mostly from ice. And so that validates our problem. So we also researched prior solutions, and we found the 4 best solutions currently for this problem are de-icer sprays, ice scrapers, heated wiper blades, and windshield covers. So we used these solutions as inspiration for our own, but also found many cons with these solutions. So for the de-icer sprays, many of them contain chemicals that are toxic and can negatively affect people, especially pregnant women. And for ice scrapers, we found that in order to clear your windshield, you have to stand outside in the cold and physically remove the ice. And for older people and people with disabilities and people like me that it's hard for them to scrape the ice off the windshields. And for heated wiper blades, they're only available in really expensive cars and luxury vehicles, so not many people can afford them, although they are very efficient. And for windshield covers, the user has to remember to put the cover on the night before and to remove it in the morning, and also have to worry about storing it and folding it up. Okay, so after viewing these solutions, we created a decision matrix and decided that the best current solution was the windshield cover because it prevents ice instead of removing it, and that will eliminate a lot of time that could end up making people late. So we wanted to innovate that design, but create a new one. So we brainstormed many ideas of a new cover, but we wanted to make it retracting, so it's most user-friendly. So we had 4 main designs. You can't really see, but the first one was like an awning, and you would press a button and the cover would like shoot out over the windshield, and press a button and it would come back up. Our second idea, which ended up being the design we went with, where the windshield cover would flip. So it would start on the glass and then flip over onto the roof. And our third idea was like a drawbridge where strings attached to the cover. And the fourth one was like slat blinds, where there'd be like blinds coming over. But we found that most of these designs couldn't work because if the strings freezed over or the actual windshield freezed over, then it wouldn't be able to roll up or come out over the windshield. So the flip design ended up being the most viable, so we decided to go with that. And next, Cole will talk to you about building our prototype.
Okay, so we started building our prototype by building models using straws and cardboard and paper to just get a feel for what we wanted to do with the flip method that we decided on. And we also did an inventor drawing to help us kind of get a look for what we wanted to create. So when we built our prototype, we decided to use PVC metal for our tube and PVC pipe for our tube, and we used metal provided in the classroom for the roof type thing that it would sit on. And go back. And we also used a cover for reflectors for the windshield as our cover for the windshield. And we ended up using a motor and Arduino for our prototype to code it. Okay, so when we tested our prototype, we did 3 tests. The first test was a frost test. And on one side of the windshield, I left it up and I applied a solution with Epsom salts and water and dish detergent, and it created this salt-type mixture, or this frost mixture that when applied to the car, in a few hours it would turn into like a type of frost. And so I applied it to the one side of the windshield without the cover and to the other side of the windshield with the cover on. And on the side without the cover, it showed up pretty much everywhere that I applied it. And on the side with the windshield, it only showed up in a very little strip on the top. And while testing this, it rained, and it gave me an idea for another thing that could be a potential issue. So basically, when it's in the winter, when it rains, if it seeps through and then freezes over, it could freeze onto the windshield, which we're trying to prevent. And it ended up actually seeping through just a little bit on some of the sides, which can be an issue. We also tested the motor during freezing because during the winter time, it would most likely freeze over, and we needed to test to see if the motor had any like drop off in performance. And I tested it for 30 minutes, an hour, and then overnight, and there was no change in the performance of the motor. Okay, so the end goal for this project, if we had more time, we would definitely want a roof rack with clamps that would actually like clip onto the car. We would also want to get a little bit of an updated motor to have the power to be able to consistently flip the windshield. And overall, we would just want this design to, and also use a different cover material that would make it either water resistant or just add like a thing on top of the cover to make the water not be able to seep through. And our acknowledgements, we want to thank Ms. Carroll and the engineering team panel for giving us input for pretty much everything and guiding us for our ideas for this test. And while brainstorming for our final design, we were all giving input to each other, and Owen actually gave us the input for the flip design that we ended up going with for the car. And the next group is the plastic pollution group.
Hello, I'm Scott Warner. I'm going to Purdue University and studying hopefully aerospace engineering.
I'm Sean Casey. I'm going to Virginia Tech to study engineering.
I'm Jonah Mikulski, and I'm going to the University of Tennessee to study business, and our product is called Booms and Bridges. We would first like to start off by thanking Ms. Carroll, all the administration, all the engineers, and everyone who sponsors this program.
Plastic. Ever since the invention of plastic in 1907, humans have fallen in love. We use, consume, and throw away plastic every day without a second thought. Take a look at some of these products listed above and think about when the last time you used one was. Was it this week? Did you use one today? Do you have a water bottle with you right now? So one of these products that stands out to me is the plastic straw. Every day in America alone, we consume 500 million plastic straws. A plastic straw takes 500 years to break down in an environment.
Okay, so since the year 1950, there have been approximately 8.3 billion tons of plastic that have been produced in the world, and only 9% of that has been recycled. We all know that we have to recycle, but a lot of times what happens is it accidentally ends up in a trash can, and then where does it go from there? So actually, I got caught off, but 79% of all plastics end up in landfills, and we all think of landfills as these prisons where all the trash that goes there is kept there forever, but in reality, a lot of times they're open fields where a gust of wind can just blow plastic and trash right out of the landfill. And a lot of times what happens then is these plastics are blown into creeks and streams, and then they lead into rivers, and the rivers eventually lead them to the oceans. From there, plastic leads into the ocean where it's able to come together and stay together according to currents. And what you see on the picture there is the Great Pacific Garbage Patch, and that's right in the middle of the Pacific Ocean. And due to the currents out in the Pacific, it's basically a giant circle. So all the plastic that gets into the Pacific eventually finds its way to the center where it builds up there. And it's actually roughly the size of Mexico, if you can believe that. So this just shows the rate that plastics are produced. You can see since 1950, it just grows exponentially and exponentially. And so eventually, this is going to come to a breaking point where we can't do anything about all the plastic that's out there in the environment, and it all ends up in the ocean eventually.
Okay, so I'm sure you've come to a conclusion by now that we have a problem with plastic on our hands. And the main source of this problem is how long it takes plastic to break down naturally in its environment. And so as you can see, a fishing net would typically take about 600 years to break down fully, a water bottle about 450 years, and a very light plastic bag about 20 years to break down. And as these plastics break down, they just transform into smaller and smaller pieces of plastic, which can find their way into the deepest depths of the ocean. And plastic has actually been found in the bloodstreams of marine life in the deepest point of the Pacific Ocean, if you can believe that. And if we continue on our current if we continue producing plastic like we are today, the amount of plastic in the ocean will outweigh the amount of marine life in the ocean by the year 2050.
So why is this a problem worth solving? So we all know the immediate effect of plastics in the ocean is that they can entangle marine life, endangering species. But what most people don't know is that when plastics are in the ocean, they break down into what is called microplastics, which is a plastic sample less than 5 millimeters. So once the plastic polymers are bonded together, they are never able to biodegrade again, which means that every bit of plastic we've ever produced is still in our environment somewhere today. So plastics enter the ocean, they break down into microplastics. Fish consume the microplastics, it enters their bloodstream, and then humans consume the fish that have the microplastics in their bloodstream. So essentially, we are eating our own pollution. And the health effects of this are unknown yet because they have not been studied much, but I can't imagine it would be good. So if we continue on this rate, our dinner plates could end up looking something like that.
Okay, so once we decided on the problem of plastic pollution, and specifically in the ocean, we came across 3 different avenues through our research. Basically, we could focus on the removal of plastics from the ocean where it already is. We could focus on preventing the plastic from reaching the ocean. And we could also focus on changing plastics and basically changing an entire industry so that plastics would break down long before they could ever get to the ocean. So a couple of solutions that we came across once we decided on the prevention of plastics from reaching the ocean is this first one's called the Baltimore Harbor Trash Wheel. You might also hear it as Mr. Trash Wheel. It's in the Baltimore Harbor, which was very heavily polluted about 10 years ago, and they decided to do something about it. So essentially it works. It's basically, if I can get the laser pointer to work. So this is basically a giant treadmill, and this corral keeps all the plastics in, and it just sucks up the plastics and leads it to a dumpster on the back. This next one's called Sea Bins. It basically just works like a trash can in the ocean where it works with tides and creates a vacuum that sucks the plastics in. And then there's also something called the Ocean Cleanup, and it uses booms, which are commonly used in oil remediation. And booms float on top of water because of their density. So it just helps corral things in, things like oil, things like plastics, which are less dense than water, so that you can collect them all in one area and then you can help remediate the problem after that.
To put our project, our idea in terms of a simple analogy, so imagine you walk into a room and there's a faucet running with water. The water is overflowing in the sink and it's creating a flood all around on the floor. You have a bucket and a mop. What do you use first to clean it up? Most of you would probably think the bucket, but the correct answer is to turn the faucet off. So imagine plastic being the water that is flooding into the ocean, and a lot of these organizations are focused on cleaning up the plastic that's in there, but if we don't catch the problem at its source, then it will continue polluting the oceans. So this is our solution.
Okay, so with our solution, we decided to use a couple of things to our advantage. Number one is the fact that most plastic floats at or near the surface of water, and so we can use booms on the surface of water, which are basically giant inflatable tubes that guide the plastic to wherever it needs to go. And we use existing infrastructure of bridges on most rivers around the world that the booms can be attached to the base of the bridges and guide plastic into very specific spots, such as the one up there. So you can have booms on both sides of a river and take away 2/3 of the plastic exiting the river. Once the plastic gets into a designated really small collection area, we can have a conveyor belt that's modified like this one, and you can see the very small baskets that are made of metal mesh that allows water to move through them very easily, but they still pick up trash. And you can see it working here, picking up our miniature water bottles and dumping them in the trash where they belong. And that's pretty much the concept of our design. It can be turned on once or twice a day or as needed, as the current of the river allows plastic to drift into those very small collection areas. And if there's an excess of plastic, we can just turn it on whenever we need to.
So potential and benefits of booms and bridges. It can be constructed worldwide anywhere there's a bridge on a river. It significantly increases the cleanliness of coastal communities, uses minimal energy, which can be provided using a solar panel on top. It needs to be cleaned rarely, as we will have a light sensor on top in the large-scale design that would trigger it night and day. It would run for a certain time interval to pick up the plastics that have accumulated, and it's simple and cheap to construct. And so the reason we picked rivers is because 90% of ocean pollution from rivers comes from just 10 rivers around the world. And a few of these rivers that we could do are, the most polluted river in the world is the Citarum River in Indonesia. As you can see, you can't even see the water in there, it's just all plastic. 5 is the Marilao River in the Philippines, also just complete trash. And number 10 is the Mississippi River in the United States. So this is a localized problem that is not just at other areas of the world.
So essentially, it would be a lot easier if we could just say everyone recycle, everyone cut out plastics, but we know that that won't happen. So what we want to do is just limit the amount of plastics that are reaching the ocean, slow down that rate, so then eventually we can reach a point where we can actually go out into the ocean, remove the plastic from there, and it'll actually be able to make a difference because the plastic won't be getting replenished at a rate quicker than we can remove it.
The plastic you use once tortures the ocean forever. Thank you.
So can you tell these kids are going to go out and save the world? Let's give them all a round of applause. Great job, everyone. Now I'd like to introduce Mr. Dave Mayer to come up and talk about our group.
So I get to do the fun part. They had to do all the work. So my role here at Seneca is I'm an assistant principal. I supervise mathematics and science. I also supervise the Project Lead the Way program. And I couldn't be happier for these students. And I think, I know we've clapped already, but I think they deserve another round of applause for coming up here and presenting to all of you. So I want to thank them, the students, for their perseverance, their hard work. They have sacrificed a lot, and it shows. Thank you, parents, for your dedication to your students. They have reached this milestone, and you are a major part of that journey. I remember when we chose this class. For those of you that don't know or don't remember, there's a process to the application where students show interest, and then we have certain spots, and we choose kids. And I remember hearing and thinking about and seeing these names 4 years ago, and now here they are ready to graduate, and I'm very proud that they've come this far, and they're ready to clearly go on and save the world, and either major in engineering or maybe major in business, and do whatever it is they're passionate about. So to the students, I just want to say that you started out as 24 wide-eyed freshmen. There are 15 that remain. The PLTW staff here at Seneca are proud of you and what you've accomplished. No matter what major or university you've chosen, I know that the future is bright for all of you. I'm confident that you learn the skills that will help you no matter what profession you choose. So, Seneca High School Engineering Class of 2019, please stand. Mrs. Carroll and the other PLTW teachers have assured me that you have met the requirements to graduate from the Seneca High School Project Lead the Way engineering program. It is my pleasure to be the first person to say to you, congratulations. As a memento of your hard work and dedication to finishing what you started 4 years ago, Seneca High School would like to give you a cord to wear at graduation on Monday. The cords are teal and white, and they match the colors of Project Lead the Way. I'm going to ask Mrs. Carroll to come back up to the podium. She's going to call your names. What you're going to do is come up the stairs. I'm going to be over there. You're going to grab a cord. Actually, I'm going to put it around your neck. And then you're going to proceed over to the left-hand side until we get everybody to have their cord.
Okay, congratulations to all of you. First, we're going to bring up Colin Boisvert. Sean Casey. Taya Gilliland. James Hill. Brendan Jaggard. Scott Johnson. Jonathan Clank. Owen Lovett. Cole Ledwikowski. Jonah Mikulski. Shannon Preble. James Pronchik. Robert Sunbury. Dustin Termy. And Scott Warner.
So I just want to say Mrs. Carroll has done an amazing job, continues to do an amazing job with these kids. To come from what they have done, I remember sitting in her class early in the year and they were brainstorming, and now to have these projects in fulfillment is amazing. So we're happy, and I'm thankful for her and the other Project Lead the Way teachers that I know are here and all their hard work. The other thing I want to say is in the cafeteria, we have a poster session that you're all invited to. We also have some refreshments so you can see up close the prototypes that they have made. So please come down and enjoy talking to them and seeing them. Parents, you're free to go up and grab a picture, okay, of the class. I know I'm going to. So that, all right, we're done. That concludes our program, and the poster session will start down in the cafeteria. Thank you.